Good day, statisticians. And here we're going to have a quick video that recaps the idea of a geometric random variable, which actually, when I'm thinking about it, might even be the first time that we really formally spoke about geometric random variables, though we've actually seen them a couple of times in a sort of background way. So this will also help us review random variables and binomial random variables along the way too. So if you recall, when we were talking about random variables, a random variable is fundamentally some type of variable, right? It's a variable where the outcomes occur through some type of chance process. The outcomes are through a chance process. And here, if I can just manage to write a little bit more slowly, maybe you can read what I wrote here on this fancy little graphics tablet, right? So a geometric random variable is just a subclass of this. Any type of situation, if you roll a die and you observe the number on the die, then that outcome would be some value that occurs through a chance process, right? And so, like if you got a 6, there was some probability that determined that. Okay, so geometric random variables are just sort of along these things, and they're going to be kind of similar to binomials. But let's start with an example to help us get them. Whoa, that's not what I intended to do. Let me zoom way back in there and zoom in some more. Oh my gosh. Let me zoom out just a little bit, and here we go. Suppose we had a football kicker that makes 40% of his field goal attempts from 50 yards or farther, right? And let's let X equal the number of attempts it takes for the first successful field goal. Okay, so that's great. When we first look at this, this might sort of remind us of a binomial, right? In a binomial random variable, you have your variable defined. Let's say we had defined y. It was the number of successes, right? Successes in n trials, right? So where n is some fixed number of trials. So is that how our x is defined here? No. Now, if we take a look, we see it's the number of attempts until our first success. So in an interesting way here, we actually have here a fixed number of successes instead of a fixed number of trials, right? Remember if we talked about bins, right? Which were the 4 things that you needed to check to make sure that something fulfilled the conditions of a binomial. First, you needed to have binary outcomes, right? Then you needed to have independence, right? Independence between our trials. Then we needed to have a fixed probability of fixed number of trials, and then finally a fixed probability of success. If only I could write here. I'm having some trouble. I apologize. It's not so great. The computer seems to be working a little slow too. There's a lot going on. But anyway, we have a fixed number of trials, a fixed probability of success. This seems to fulfill basically all of the conditions except for the fixed number of trials, right? We can assume that there is a fixed probability of success, 40%, right? And we know in this case how many successes we're trying to find. In this case, we're looking for just the first success, right? But we don't know how many trials it's going to take to the first success. You know, we could go on forever, right? I mean, you could have a field goal kicker who just keeps kicking field goals over and over. Well, keeps kicking field goals. He keeps attempting field goals over and over and over again and just simply never succeeds, right? And so this is not a binomial because we don't have a fixed number of attempts. You can have a near infinite number of attempts. Technically, you could have an infinite number of attempts if you were just never successful. It could happen. So, all right. How would we think about this scenario? Well, of course, so we're going to call this a geometric. And a geometric fundamentally has only one parameter, right? A variable, let me rewrite that. If we said some variable x is geometric, and usually we write like geo or ge to represent that. There's really only one parameter for us to think about because there's no fixed number of trials. It's just the probability of success, 40%, right? And so then we could calculate probabilities based on this. Like you might wonder like, okay, what's the probability that x equals 1? That would mean the probability that someone kicks the field goal in their first attempt. Well, since there's a 40% chance of success, it seems pretty obvious that should just be 40%. The probability that you'll make your first field goal is going to be 40%. Well, what's the probability, say now, that x equals another number. Let's pick another number. Let's say 3, right? In other words, this would mean that the first time someone made their field goal happened on the third attempt. Well, in order for the first field goal to be made to be in the third attempt, that would mean the 2 previous field goals had to have been misses, right? So there was ultimately 3 things to think about here. Uno, dos, tres, right? And so the last one, we're actually going to make the field goal. That had a 40% chance of happening. But the previous two, were both misses. So I'm going to get a slightly different color there. There's a 60% chance, do you agree, that in either of those two previous trials that you would have missed the field goal, and on the third trial that you would have made it? So the probability that x equals 3 is going to just be 0.6 squared times 0.4. Right now, we could go in our calculator right here and see what that is. We could do 0.6 times 0.6 times 0.4. I don't know why I quite did it that way, but we see it's 14.4%. So that's kind of nice, right? That's a fun fact to know. That there was, let me move you out of the way, get out of the way, the color editor, right? This is approximately 0.144, right? And in general, you could see that if I just change this to some other number of trials, say, what's the probability that the first time the field goal kicker made it was on the 10th trial? I could just change that to 10. And then there would have had to have been 9 times that oh, that looks almost like, that doesn't look like an exponent anymore. Here, let me hit the undo button. I like that, undo, right? I could change that to 9 misses, and then the next one would be a success. And so now the probability that you missed the first 9, but you finally made it on the 10th would be like 0.6 raised to the 9th power times 0.4, and stupid calculator, 0.6 raised to the 9th power. That's, you know what? That's one of the reasons why I just like using physical calculators instead of these digital ones, because I don't know, I always mess up how I type it in. But there you go. You can see that that is that's a pretty low probability. There's only a 0.4% chance that you'll actually get your first success on exactly the 10th trial, and the previous 9 were all misses, right? So that's kind of nice. In general, maybe you can anticipate here that there's a nice, a little general formula that we could use for a geometric, right? That in a geometric random variable, let me make some space. I'll kind of go over here, right? Whoa, I keep hitting the button to just, oh no, I'll get better at this over time. But in general, when we talk about a geometric random variable, we can say that the general form for a geometric, if we have, let's say y is some geometric random variable with the parameter p, then I could say the probability that y takes a particular value, in this case, let's call it k, will simply be the probability of failure. So there would be 1 minus p failures, and how many failures will be k minus 1, and then we'll multiply that by p, right? And that'll just be to the first power. So you don't even really need the first power thing here, but one of the reasons I write that is so that you could see, oopsie, there's my delete thing, so that you can see that the total number of trials should add up to k, because remember, k is really fundamentally a number of trials. Our variable here is the number of trials, not the number of successes. So this means you have to have k minus 1, k minus 1 failures, and the probability of failure is 1 minus p, and then you have your final success. So it's almost easier just to intuit exactly how to calculate these things here, just like that. So anyway, that's I keep doing that, and that kind of annoys me, and I'm going to get used to it. So you can kind of see where I'm going to be going with stuff. Isn't this fun? The first video recording this way. So anyway, we're having some fun. So let's think about this. Just like whenever we talk about random variables, in addition to just thinking about the actual value of variables and how to calculate probabilities, we talk about the distribution of a variable. And if I ask you to describe the distribution, remember there's at least 3-4 things you need to describe. The shape, the center, the spread, and then you can describe outliers if you have a particular data set. But in general, we could try to imagine what would be the distribution of this situation. What's going to happen to the probabilities? Well, I calculated it earlier, and here, this actually is the distribution. I'm going to move myself. I'll just go over by the calculator now. You don't really need, we don't need the calculator right now. But what I did is I used Excel to help me facilitate doing this more quickly. And here is actually the whole distribution for the number of trials it takes to the first success here, right? And so we actually see that the distribution of this geometric, and in fact, we'll see all geometrics if we really think about it, all of these guys are going to be skewed to the right, right? A skew to the right distribution, because you're always going to be most likely to find your first success on the first trial. And then all the successive trials, it's always going to assume something else happened before it. So for instance, here, if I look at this table here, right, that if I'm thinking about, say, the probability that x equals 4, because remember I used my variable as x right there, right? Let me make that a little bit bigger, x equals 4, right? Then say I looked at x equals 4 right there. This presumes that something else happened on the first 3 trials, that I had a failure, a failure, a failure, and then finally had a success. And so the probabilities are always going to go down because every single time you have a higher value of your number, it's going to presume something else happened on those previous trials. It's always going to be a skewed right distribution. Now, so in all geometrics, we'll have something that's right skewed. So the shape of all these guys is going to be skewed right. Right? Well, that says skewed, and you just believe me, right? Now, we're going to see that in terms of the center, that all of these distributions are going to have exactly an expected value of 1 over p. The expected value of x is going to be 1 over p, or we could always write that in terms of mu. It's always going to be 1 over the probability of p. So, for instance, in this case, since I had, I'll put myself over here, since I had a probability of success of 40%, I'd say 1 divided by 4, that's 40%. Well, if I took the reciprocal of that, that's 4. That would mean that, did I do 1 divided? I said 40% is 1/4. What am I even thinking? Well, 40% is 2/5. I'm just being silly. 2/5, which is 0.4, then the reciprocal of that is 2.5, which would mean on average, it should take me 2.5 attempts to have the very first time that I'll actually kick a field goal if I was this kicker, right? And so that's our center. It's always going to be 1 over p. If you think about it, if you were flipping a coin, right, how many times on average do you think it would take you to roll a 1? Think about it. How many times on average would it take you to roll a 1 on a coin? Well, on a coin, again, this is a different scenario now. If you think about a coin, right, did I say roll a 1 on a coin? I mean on a die. What is wrong with me today? If say you had a die here, right? And how many times will it take you to roll a 1? Well, since the probability of rolling a 1 of a 1 is 1 out of 6, right? Then it should take you on average, the average number of times is 6 times, the reciprocal of 1 out of 6. And that's kind of intuitive when probability is simply 1 over a number, right? That the average number of times it takes to have a success is just 1 over the probability. But in this case, since it was 0.4, the reciprocal of 0.4 is 2.5. So that's kind of nice. Now, we could talk about the standard deviation of a geometric random variable, but you know what? It's not something that technically we need to know for AP Stat. But anyways, I could still help you guys out here a little bit. Here, let's see here. It's not something that you technically need to know, but the variance of, oh my gosh, let me switch my pen back. The variance of a geometric random variable is going to always end up being, what is it? I'm drawing a blank. Oh yeah. 1 over p squared, right? Now that's kind of fun. Then you can take the standard deviation of that the square root of that and give you your standard deviation. That's a fun fact. That's not something that we need to know for AP Stat, but that would round out our whole shape, center, and spread thing. So, okay, that's kind of nice. So let's just look at some problems where we actually do some stuff for geometrics instead of just kind of talking about these. Remember that we're defining our variable as the number of trials till our first success here. So let's go down here. Here I have, isn't this fun? Here I have some examples here. I'm going to take my face. I'm going to move it over by the calculator for the time being. All right. So say we have this situation. Say police estimate that 85% of drivers now wear their seatbelts. That's good. Maybe more should, but whatever. They set up a safety roadblock, stopping cars to check for their seatbelt use, right? And a success is stopping a car and finding someone without his or her seatbelt buckled. I don't really find that to be a success, but remember that how you define a success when it comes to the probabilities is really arbitrary. It just depends on finding what you're looking for. And I guess cops are looking for people not wearing their seatbelts. So anyway, that's kind of fun. So let's answer a couple of quick questions. On average, about how many cars do you expect to stop before finding a driver whose seatbelt is not buckled? Okay, so in this case, notice that I'm looking for the number of trials, again, to my first success. How many cars do you expect before finding a driver whose seatbelt is not buckled? So this case, I'm going to go down here. I'm going to define my variable. I like using y for geometrics. You don't have to, but I don't know. Why do I do that? I don't know. I just like using y. But I'm going to say y is a geometric random variable where the probability of success is 0.85, right? And so if I'm trying to say on average, how many cars would I expect? Well, I kind of gave you a cute little formula before that the expected value of y, since it's geometric, should simply be 1 over p, right? And so in that case, I could go to my handy dandy calculator and let me move my face, right? And I could say 1 divided by 0.85 should be the, okay, look at that. If there's an 85% chance of success, then on average, right, it should take me about 1.176 times, right, to find a car where someone is not wearing their seatbelt, right? Wait, hold on. I'm doing this backwards. If I'm looking for someone not wearing their seatbelt, then is the probability of success 0.85? No, because that's the probability of someone wearing their seatbelt. We have to be careful. Do you like how, will you go away? And so, let's go back and let's realize that actually when I define my random variable y, I can't say that the probability of success is 0.85. The probability of success is 0.15. So think for a second. If the 85% of the cars are wearing their seatbelt and I'm trying to look find the people who do not have a seatbelt buckled, then I'm looking at a different, I define my variable wrong. So let's go back. That should really be 1 divided by 0.15. And Shazam, now we're talking, we're really saying that on average it should take about 6.7 cars till I find the first one with someone not wearing their seatbelt. So that's kind of fun. Did I make that mistake on purpose or was it an accident? You'll never know, will you, right? But that's important for us to be thinking about how we understand our facts there. Okay, so very good. Let's do B real quick. What is the probability that the first unbelted driver is the sixth car stopped? Okay, so if I want to know that it's the sixth car stopped, which is the first unbelted driver, I'm going to move this over here. I'm going to do some work on the side. Then this would mean this is the probability that y equals 6, right? And so then in general, that should simply be, well, let's see here. That would mean I have the 1 minus 0.15 is 0.85, right? These are all the belted drivers. And that should be to the fifth power times 0.15 to the first power, because I have all these, I have 5 cars of people wearing their seatbelt the way they should, and then I finally have one that doesn't. So I can just go on my calculator here, I'll move myself again, and I'll say that should just be 0.85 to the fifth power, make sure I go over, times 0.15, and Shazam, that should be a probability of 0.067. So about a 6.7% chance that the first time I find someone like that is in the calculator. So, is the first time I find someone without their seatbelt on is that. Now, there's another quick trick that I want to show you too, that instead of me calculating things this way, I could have used a trick in my calculator. Just like we saw with binomials and all those, we had a PDF and a CDF, a probability distribution function, and we also had a cumulative distribution function. We ended up having the exact same things for a geometric, right? So if I go in my calculator and I hit second vars, and I scrolled all the way down to the bottom, all the way down, here we go, geometric. See here, F and G in mine. It might not be F and G in yours, depending on what type of TI calculator you have. But if you go to geometric PDF, that would be for the probability of exactly something. And I typed in 0.15 is my probability of success, and I typed in my X is 6. I could just hit that, and Shazam, I got the exact same answer, even faster. So know that these PDFs and CDFs exist. I just want to throw that out there because it'll come in handy in some other examples. So, all right, let's just do another question. Then in C, what's the probability that the first person without a seatbelt is the 11th car stopped? Oh, well, how nice. This is just the probability that y equals 11. And so once again, let me cheat. Let me just go into my calculator. So that would mean that would be the same thing as geomet P PDF, right? And notice again that I'm doing PDF here. And I would type in two things. I type in the probability of success, which is 0.15. All right, oops, actually, let me label my inputs a little bit better. So that would be a probability of, what is going on there? I don't want you. What is going on? I don't want you. The probability of success is 0.15, right? And the number of successes would be y equals, in this case, 11. And if I put it in my calculator, let's see here. I'll just go to my calculator now. I could just write out the formula again. That should just be 0.85 to the 10th times come on, stupid calculator. That's just going to be 0.85 to the 10th times 0.15. But if I'm lazy, I could just go to the calculator and put 11. And whatever it is, the answer should have been to 2.95%, or about 3%. And so let's see here. Can I move you? You're not going to want to move. I'm just going to erase you. Can I erase you guys? Do you guys mind if I erase it? I always ask you if I can erase, and you pretty much always don't say anything. So since no one's saying anything right now, I'm going to erase that just to get it out of the way. And I'll write our answer here. This is really an inefficient use of my time. I could have just done this way quicker, 0.295, but there you go. Okay, so now a couple more questions. What's the probability the police find the first unbelted driver within the first 10 cars? Now notice the phrasing here. It says within, right? I'm zooming on that. Within. So within means it wasn't on the 10th. It wasn't exactly on the 10th. It was within the first 10. So this is going to be the probability that y is within the first 10 would be less than or equal to 10. Now, this would be annoying to calculate, right? This would mean like calculating that it happens the first time, the second time, the third time, the fourth time, all the way up to the 10th and summing them. You don't want to do that. This is where we're going to be very happy that our calculator has a CDF function. So we'll go to our calculator, and I'm going to go to second vars. Once again, I'm going to go to Geomet CDF. I'll put in my P, which is 0.15. I'll put in my X. In this case, since it's within the first 10, that's exactly how CDFs work. Remember, CDFs are always less than or equal to things. The number, it's the sum of all the probabilities from whatever the first probability would be up to whatever you plug in. So in this case, Geomet CDF would work right here. In fact, I'll write that down. So we'll end up getting This is the same thing as, let me switch back to this guy, to Geomet, and this Geomet, in this case, CDF, right? We're doing a CDF, and again, we'll do a P of 0.15, and this time Y is less than or equal to 10. That's the way the thing works, right? And we got an answer of 0.8031 approximately. So an 80.31% chance that it would happen within the first 10th. It could have happened the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, or 10th, and all of those are included in this particular event. It was a Geomet CDF. And then finally, what's the probability it takes at least 5 cars? At least 5 cars. Ooh, my, that's not what I wanted. I wanted one of these types of pens. Right, there we go. At least 5 cars to find the first unbelted driver. Well, the probability it takes at least 5. This is, again, a situation where we'll think about a CDF. Let me go over here. This is going to be a situation, so for this particular problem, we'll say this is the probability that Y is at least 5. That'd be greater than or equal to 5, right? And so I'm going to convert that over to the less than or equal to statement. So that'll be 1 minus the probability of some less than or equal to. So if you want to take a second and think about it, at least 5, that would be like 5, 6, 7, 8, all the way up to potentially infinity. So what isn't it? Well, it's over here. Here's 4. If I could write more neatly. Oops. All right. 4, 3, 2, etc. Right. We want everything from, this is our answer right here. So we want to get rid of everything that's 4 and lower. So this would be the 1 minus the probability that X is now less than or equal to the number 4, right? Not necessarily, so anyway, not necessarily what. Just remember that we have to convert over there like this. And so when I go into my calculator and I calculate this, I'll do Geomet CDF with 4. And so I'll do the same kind of thing. And if I just scroll up and just change that guy to a 4 and then hit the delete. Oh, what just happened here? Quit. Oh my gosh. Ooh, 40. I don't want 40. Oh my gosh, I don't want 40. Let me get rid of the 0 here. You're like, oh my gosh, can't you just finally get this done already? Boom. So that's about 0.477. Ooh, that's anyway, it's about 4780 if we round it appropriately. I think I just rounded appropriately, yes. And so there you go. Geometrics are very simple, especially in the way that we'll assess you for the most part. Particular problems can get kind of interesting, and we'll look at some interesting problems that I'll assign to you. There's actually a really nice free response question from the AP exam a couple of years ago that involves geometrics that I really love that I'll throw out there for you to think about. But geometrics are beautiful. They're a nice corollary to thinking about binomials. The geometric, and remember, unlike a binomial, has a fixed number of trials as opposed to a fixed number of successes. Did I just say that? No. A geometric has a fixed number of successes as opposed to a fixed number of trials. And a particular geometrics always are looking for the first success. Just as a fun fact, if we were to be studying probability in more detail, we might look at the whole series of something called a negative binomial. And a negative binomial random variable then allows you to have different numbers of successes, say like the 4th success or the 10th success, and an optional infinite number of trials. And so you can kind of have some of that stuff, but we won't do any of that stuff here in AP Stat. Anyways, I hope this video was helpful for you to figure out how to do some geometrics, and I will be with you guys soon. Have a beautiful day, and I'll catch you on the flip side. Adios.